evening, everyone. My name is Derek Liu, and I'm a rising senior at Langley High School. Today, I'm with my partners Elizabeth No, a rising senior at James Madison High School, and Jesse Zhong, a rising junior at Gilman High School, as part of the program BranchOut. BranchOut is a nonprofit program with various education leaders that was co-founded by Dr. Yuxian Wu and Mr. Richard Wang in 2015. It's grown from 20 students, volunteers, to over 150 student volunteers in 4 short summers. Our high school student mentors come from over 40 different schools across 5 states.
We started out as a peer STEM mentoring program, working at the community centers, family shelters, and county summer credit recovery programs, and have expanded into a community outreach program to promote cross-cultural understanding by featuring community heroes, creating research articles, and organizing career panels. As an award-winning community engagement program, we have received endorsement from U.S. Congress, including Senator Tim Kaine and former Congresswoman Barbara Comstock. Additionally, our innovative program won the U.S. Congressional App Challenge Award last year.
As part of BranchOut's goal to promote civic engagement, community, and STEM education, we are so excited to be presenting this very informative career panel on chemical engineering. The field of chemical engineering has become an integral part of our modern society. Chemical engineering is the practical application of the 3 sciences: physics, chemistry, and biology. Chemical engineers develop and design chemical manufacturing processes that convert raw materials into useful products such as fertilizers, plastics, food medicine, and many more. The advances made in the field have benefited many aspects of our lives, making life easier and more efficient.
We are delighted to have 3 guest panelists speaking today. Our first speaker for tonight is Professor Clancy. Professor Clancy is the head of the Department of Chemical and Biomolecular Engineering at Johns Hopkins University. She is also the Associate Director of the Johns Hopkins Center for Integrated Structure and Mechanic Modeling and Simulation. Professor Clancy leads one of the top groups in the country studying atomic and molecular scale modeling of semiconductor materials. Her lab focuses on researching advanced material processing and nucleation. It is an honor to have you here. Professor, would you like to take a minute to further introduce yourself or simply say hi?
Well, I would like to say hi and welcome to everybody who's on the call. It's really a delight to be here. And it's a new experience actually for me. And after this length of time in academia, it's hard to have new experiences, but having so many young folks on the call is always a delight. And I hope that all of you, that this is a signal that you're interested in science and math and technology, and that you want to keep going at it, because it's very important that we have your involvement if this country is going to keep taking its leadership position in the world. So I'm delighted to be here. I can tell you very briefly a little bit about myself. I come from a not particularly fashionable part of London, and went to college locally, which I think a lot of people do, especially if they're from reasonably low income families. So I went to London University, and then I was lucky enough to go to Oxford for a graduate school, came to the US, worked at Cornell, and then did a little bit of what I call pond hopping. I sort of flip-flopped back across the Atlantic a couple of times, and ended up being on the faculty at Cornell. I taught there for a long time, too many years to tell you about, many more than you've been alive. And but recently, just 4 years ago, I moved to the Johns Hopkins University in Baltimore, and moving is like getting a shot of adrenaline. So this has been a wonderful experience, and I'm now getting to do new things that I never thought I'd be doing. And that's one of the things that makes me feel good every morning. I'll get up and I know that there's something new just around the corner that I haven't thought about before. So thank you very much.
Thank you so much, Professor Clancy. Another one of our speakers for tonight is Professor Eagan. Professor Eagan is an assistant professor of chemical and biological engineering at Tufts University. He spent 1 year investigating catalysts by diluting alloys as a postdoctoral associate at Tufts in the IMASC EFRC before transferring to Harvard University to continue his work. Thank you for being here with us today. Would you like to briefly introduce yourself further?
Sure, thank you. And to echo what Dr. Clancy said, this is a really nice opportunity. It's great to see, all of you high school students kind of getting together and organizing something like this. It's really exciting. Other than that, I'll just, clearly state that my perspectives come from closer to, I think, a student's perspective. It's been only 1 year as professor so far, so a bit less informed by the many years. So I'm really excited to actually get my own, learn some of my own from Dr. Clancy and Dr. Glotzer. But also, I guess to hit on what Dr. Clancy said, I also, I went to undergraduate at the State School of UMass Amherst, and didn't really know exactly what I wanted to do at that point, kind of changed majors, really one time, I guess not that many. I didn't start as a chemical engineer, and if anybody wants to hear more about that decision, I'd be happy to elaborate later. But yeah, without further ado, thanks again. I'm excited to be part of the panel.
Finally, we have Professor Glotzer, who has been the Department Chair of Chemical Engineering at the University of Michigan for the past 5 years. She has done extensive research in the manipulation of molecular, nanoparticle, and colloidal levels to create design structures. Professor Glotzer's research group seeks to understand complex behavior emerging from simple rules and forces, and use that knowledge to design new materials. We are very thankful to have you with us today. Would you like to quickly further introduce yourself?
Sure, thank you very much. I am also delighted to be here to echo Professor Clancy and Professor Eagan. We always love talking with young people about career opportunities and the kinds of careers that you can have in science and engineering. My road into chemical engineering is perhaps a little bit different in that my degrees from college and from undergraduate and graduate are all in physics. So I started out and I grew up in Southern California and went to UCLA as an undergrad. I changed my major probably 5 times while I was there, just trying to find the right fit for me. And then I discovered physics and I was hooked. And I studied physics as an undergrad then, and I studied physics, got my PhD at Boston University. And then I went to do what's called a postdoctoral fellowship, where you continue to do research, but you're more independent than as a graduate student at the National Institute in Standard and Technology. It's just outside of Washington, D.C. I'm sure you guys have heard of it, being from the area. And I ended up getting a job there, and I was there for a total of 8 years before I moved to the University of Michigan as an associate professor. And one of the things that got me interested in joining a Department of Chemical Engineering was I realized that the research that I was doing and the kinds of scientific problems I was interested in lie at the kind of the nexus of chemical engineering, material science and engineering, and physics and chemistry. And as we'll probably talk about a little bit more today, chemical engineering, it brings together everything. It brings together math and chemistry and physics and biology and computer science and data science, and all of that is wrapped up into chemical engineering. And you'll also, maybe we'll talk about how chemical engineering is one of these eclectic fields where all are welcome. And so I've been now at Michigan for 22 years, and I've been department chair for the last 5. So I'm looking forward to talking more with all of you.
Thank you so much, Professor. We are thrilled to have so many knowledgeable panelists for tonight. Our team will ask questions until around 8:45, and then our audience will have a chance to ask some questions of their own. We will also be taking a group photo at the end, so make sure to put any questions you have in the chat. With that, let's begin our questions. So our first question, and this is an important one, is what first sparked your curiosity in chemical engineering? And why did you choose to pursue this field? Professor Clancy, would you like to start us off?
Yes, I would. And like Dr. Glotzer, I actually am not a chemical engineer by training either. I'm a chemist. And so I think that kind of brings home her point that chemical engineering is a discipline that makes everybody feel welcome. So what started my first interest in chemical engineering, I think, was because I met somebody who was a chemical engineer. And when I was a graduate student, and he explained to me really what chemical engineering was about. And I think there were two lures. One, the key one from a sort of technical point of view is that I realized partway through my PhD program that what I really like best is solving problems. And so it was the problem-solving aspects that seemed to be more pronounced in chemical engineering than in chemistry. The chemistry part of it I loved because it was, why do these things happen? But it was also important to me that I had something to show for it at the end. I had knowledge that other people could leverage. But I have to say the other part of it was that it was a chance to go somewhere different, and it was a chance to leave my own country and to move over here. And that was just very exciting. And so I think it was the sort of fun of the self-realization about problem solving, but then also the sort of excitement of doing something that is a little scary to do at first, which is, to leave your family, to leave everything that you know and come to another country. And I found that pretty exciting and scary. I was also scared.
So maybe I'll just jump in and pick up off of Professor Clancy. As a physicist, like chemistry, the job of the physicist is also to ask why. Why are things the way they are, right? Why are materials the way they are? Why do atoms stick together? Why does this thing have this structure or this property? But I found myself wanting to understand why, and then wanting to say, so what if we could do something more? Like, what if we could do this or do that? That isn't currently possible today, but it could be possible in the future. You can kind of see how we might get there. That made me realize that I could sort of be the best scientist I could be in chemical engineering.
Mm.
Yeah, I think from my perspective, a lot of why I wound up in chemical engineering is very similar. So I started, I had a somewhat shorter path, but in high school, I had no idea what chemical engineering was. I didn't really even know what engineering was, even though my dad was a mechanical engineer, still didn't know. But I did know what physics was. So I actually started as a physics major. But I found over time that it seemed a bit more about, as Dr. Glotzer was saying, we were spending a lot of time focusing on understanding, and I wanted to do things. And there are, that's not to say that in physics, there aren't people that were doing a lot of great things. I felt like what I wanted to do is tangibly make something. And I missed chemistry, and there's plenty of math and physics, but I ended up talking to my high school chemistry teacher, and I asked them, what I should do. I said, I like chemistry, I like math, I like physics, and I want to make something. And then I talked to him. He basically said chemical engineering is probably where you belong. I ended up talking to some people at the university, an undergrad, And they basically said, everything that you want to do is what we do. And I told them, I want to turn one chemical that's waste into something that's useful. And they said, yes, that's what we do. And I was very focused on sustainability as well. So I was thinking kind of near term. So I think we all kind of united in the idea that we really wanted to do something with the knowledge. We wanted to create something new.
Mm-hmm. And something that maybe is interesting is that Professor Eagan, in wanting to create something tangible, what distinguishes him from Professor Clancy and myself is that we don't actually make anything. We make computer models, we solve them, right? So we're computational chemical engineers, right? And so we're trying to model systems and make predictions and try to provide information to experimentalists like Professor Eagan, who then actually go make things.
Yeah, and I would not know what I was doing without people to do the theory behind it. So we have the skill sets as chemical engineers to do both of these very seemingly disparate tasks, and that's what allows for chemical engineering to kind of cohesively move together.
Okay, thank you so much for that. Next question. So for some of our audience members who are really interested in actually pursuing a career in this field, could you describe your own educational experience, kind of how you prepared to become a chemical engineer?
I guess, oh,
There you go.
sure. I mean, as I kind of said before, I don't really think I prepared. I mean, this isn't particularly useful, but I kind of like fell into the things I was doing. I liked chemistry in high school. I liked physics in high school. I kind of just went with the flow. I didn't really look for any opportunities. I wish I had tried to find some more opportunities when I was going through high school. But then once I got to a large public university, there were so many opportunities that I just kind of looked for things, talked to people, and kind of just went with the flow in some cases to just kind of see what opportunities are out there. So the one thing I've mostly learned over, a fairly short career so far is to just look out for opportunities and just kind of give things a shot, because you never know what you're actually going to want to do until you try some stuff.
Mm-hmm. Paulette, do you want to? I thought you were going to speak, so I was waiting.
Well, not being a chemical engineer, I kind of came late on the scene, and I think that I was really a sort of fairly rudderless through my undergraduate career. I did what people said was a good idea because I didn't have a whole lot of direction myself. In fact, I'm always very impressed by undergraduates who know what they want to do and just have a real sense of it. So I think it's okay to sort of release yourself from that burden of feeling like you have to know where you're going. You really don't. You'll find that when you need to do things that you enjoy doing. If you don't enjoy doing it, don't do it just because you think that it pays a lot or it looks good on your resume or whatever. Just do the things you love and you really can't go wrong. And then you'll sort of either it'll take you a short term or a long term, but you'll get there. You'll find what you really like to do. Mm-hmm. So I think you have to kind of let your heart be your guide in a lot of this.
I feel exactly the same way. You can say, well, if I want to be a chemical engineer and I want to go work, say, in a traditional chemical engineering industry, you want to go work for ExxonMobil or 3M or Dow Chemical, et cetera, then you should go get a bachelor's degree in chemical engineering. You don't have to have one to work there, but that will prepare you perfectly for jobs in that sector. But if you're thinking, well, I might want to do other things. I might want to do science. And, you know, one of the things that you're getting from talking with the three of us is that we're professors, right? And we live to do research and to teach, right? And to teach our students how to do research. And so I don't know about the others, the other two faculty, but I think of myself more as like a professor than a chemical engineer. So when I was, you know, going through and learning stuff, I was never thinking in terms of, oh, I need to prepare, like, what do I need to know to do this, this, this. I just voraciously studied everything that I was fascinated by. You know, if I look back, I should have taken more math, but I didn't, but that's okay. I took enough. But I never really said, okay, what do I need for something? I just did what was interesting to me, what felt compelling to me. And if I had just followed some sort of recipe, I would never be where I am today, I think.
Mm-mm.
I fully agree with what both Dr. Clancy and Dr. Glotzer said. That resonates a lot with kind of the way that I kind of found where I went. And in the end, I think you kind of get conditioned throughout, you know, elementary school, middle school, high school, undergrad, that you're preparing for your next step. There's usually kind of a series of check boxes that usually can get you to where you want to go. But once you leave undergrad, the check boxes are gone. There's really no clear direction necessarily anymore. So if you kind of go through this attitude of how do I do everything exactly right, you'll wind up at a point where, well, I did everything right, but I don't know why. So following your heart and following what you want to do, very much, I think, you know, in chemical engineering, it does, you know, usually the salary is good enough, is fairly good. So you're also fairly safe, I would say, in that decision. But yeah, follow your heart.
I think chemical engineering undergraduates come out with the highest starting salary. I don't know if that's the same anymore relative to computer scientists, but compared to the other engineering disciplines, mechanical, electrical, you know, material science engineering, naval, all of that, chemical engineers start with the higher salaries with a bachelor's degree.
Thank you very much for your answers. As someone who's not too sure myself what I want to do yet, it's reassuring to know that I don't need a concrete plan. So for our next question, how would you describe a typical day for you, and what exactly do you do on an everyday basis?
Oh my God.
I never have a typical day.
So, you know, there's a TV show, I don't know if they pulled it after one season, that it's called The Chair. And it's like the life of, have you seen this with,
Yes.
What's her name? Sandra Oh. Yeah, it's about the life of a chair of an English department. And you know, talking with my fellow chairs, we joked that, well, if they were really going to do a TV show on the life of a chair, it'd be pretty boring because they'd be sitting there for 4 hours watching us compose emails. But I won't tell, like, a typical day is I'm on my laptop like almost all the time, or I'm talking with people, right? So, you know, as a professor, I'm talking with my students. I'm meeting with my PhD students and my postdocs, and we're talking about their research projects. And that is my favorite thing of all to do, is to talk with them and do science, because every time we're talking about science, you know, it's, you know, and I was having this conversation with someone the other day when they said, well, what's it like to teach someone like how to do research? And I thought, I don't teach my PhD students anything. I'm just doing science. We're discussing and we're throwing out ideas and we're riffing off each other. And it's almost like when it clicks, it's kind of like jazz, where it is magic. Everyone comes and they've got their own ideas and their own different perspectives and way of thinking and superpowers that they bring to the table.
Mhm.
And then someone says something and someone else riffs off of that, and then you riff off of that. And, you know, pretty soon you're somewhere with this level of understanding or excitement or idea that you would never have had like on your own, right? I think that a lot of the public thinks of scientists as we sit at desks and with books and we write, or we're in a lab, like, you know, with a beaker, but it's actually a very social experience.
Mm.
So I would say I spend most of my day, every day, talking with someone about something.
Yeah, agreed. But I think the magic, I just want to talk about that too, because I had an experience like that today, and it's
Me too.
Oh, yeah, with students, and it's just that unexpected, and you see things, it's almost like fog that all of a sudden
Yes.
condenses into something totally unexpected, and that is magical.
Yes.
And you know, I'll tell you a little story. So one of my first sort of chemistry job, if you like, was when I was an undergraduate, and I got a summer job packing columns and running carbon, hydrogen, and oxygen analysis, and I was awful at it. But I had a wonderful woman who, a young woman who was working with me. She was an undergraduate too, and she and her family had just been expelled from Uganda when Idi Amin was going on his sort of craziness. And she said that all the women in her family had been taught to tell fortunes. And she said to me, I can tell yours if you like. And I said, oh, yes. You know, I mean, I was young. It didn't matter what she said anyway. And so she said, I see you're going to have she said, over 30 children. And we just burst out laughing because it's so ridiculous. But I do have over 30 children. I have all of my students. And I bet, Sharon, you feel the same way, right?
Well, yes, I certainly do. I mean, that's what I tell them, like when they, you know, 4 of my PhD students just submitted their dissertations yesterday. That was the deadline for getting it in. So 4 newly minted PhDs. And I tell them, like, I'm your advisor for life.
Yes.
You can never fully get away
from
me. And I'm always here for you.
Yeah. And I always tell them, right home, you know, just like you tell your kids.
Yeah, so that's, you know, I agree very much with both of your perspectives. I'm coming from Dr. Glotzer talks about it being kind of jazz, and, you know, you're kind of throwing things around and things just come together. I'd say at this point in my career, the jazz is a little bit louder and chaotic, because where cool. My day is running into lab and running out of lab and talking to one person, talking to another person. It's very much trying to figure out what's going on at the beginning, and just kind of going with the flow and just seeing where science points you, because the reason that we do science is not because we understand it, it's because we don't understand it. Mm-hmm. And if I knew what I was doing, then I probably wouldn't do it. That would be boring. So we're kind of guided by this unpredictability. Mm-hmm. With all this being said, of course, we are professors, we are researchers. Our days are fairly different than a lot of people who go into industry. I don't have that perspective personally. So there are a lot of differences that I can't really speak to, but a day in the life is very much, there is a lot of time behind a computer, but there's also a lot of time just talking and meeting. So also, as was said before, a lot of the learning that a graduate student has is not in classes. Undergraduate career is very much classes and classes, and what some other experiences you get. In graduate school, you take like 10 classes, 5, something. A lot of your learning is just talking to other people and trying stuff. And that's kind of more how the world is. You kind of just communicating, talking, learning from each other, and just going.
So just to add one thing before we go on to the next question about what does a typical day look like. one of the things that I love about being a professor is that you could change your typical day.
Mhm.
Like you have a lot, we have so much freedom in our jobs. We create, the kind of typical days that we want to have, but it's the kind of thing where there's so much freedom. We travel to work with colleagues around the world and to go to conferences and to share our results and take our students to conferences. And if we really wanted to have a day of free of meetings in principle, we could do it. Like once, maybe. No, we could do that. When we get to write proposals in order to raise money, like trying to find venture capital, right? We're going to the federal agencies trying to raise money, but that's an opportunity to come up with new ideas and brainstorm new things and to change the direction of our research if we want to, right?
Yeah.
We could wake up tomorrow and go, you know what, I don't want to work on this anymore. I think I'm going to work on this over here. And you have to convince someone to fund you to do it. But you have so much intellectual freedom as a professor of chemical engineering. It's great.
And it's like you have a startup. You're always running on the verge of not making payroll. And then when your employees get any good, you kick them out.
Yeah, exactly.
Yeah, so we have another question for you. What is the most challenging aspect of chemical engineering in your opinion?
Like chemical engineering, the discipline itself, like the curriculum, or like being a chemical engineer? What do you mean?
I think specifically more like the discipline, because I know you three are professors, so it might not be as relevant to talk about the actual like curriculum and stuff, but what do you guys think is the most challenging part about the discipline?
Well, I would say that today, one of the very challenging parts of the discipline is that the discipline is so much more than it was, say, 20 years ago, 30 years ago, 40 years ago, when chemical engineering kind of came out of petroleum engineering, right? And when people think, if I stopped random person on the street and I asked them, what do you think chemical engineering is? They might think of oil and gas or, big plants and things like that. But chemical engineering today, it's everything. You find chemical engineers working on all sorts of processes, making new materials, 3D printing, additive manufacturing, using DNA technologies and developing, new approaches for immunotherapy and CRISPR and just, nanotechnology, nanoscience. And so the challenge is knowing all this stuff, right? Knowing biology and knowing chemistry and knowing physics and knowing this and knowing that, and trying to integrate that all to advance the field, I think is, it's exciting, but it is a challenge.
I think there are always bits that you like and bits that you don't like. As a chemist, I had no background in transport, so I find that the sort of least interesting and the most challenging, but I love thermodynamics. I just think that's great. And also the interplay with kinetics, the way I think of it is thermodynamics tells you if something could happen, and then kinetics tells you how long that's going to take, which is very important.
and if it will at all.
Indeed.
Yeah, both Professor Clancy and I in our research do basically computational statistical thermodynamics.
Yeah.
And to Professor Clancy's point, I do reaction kinetics. So I often have to think first about what could happen, and then I try to make that happen so I have to start with kind of the potential to make sure I'm not trying to do something impossible. And along the lines of trying to do something impossible, I think one of the challenges that you face with a field that's as challenging and as broad as chemical engineering is you get to a point where you have to accept that you will not know everything and you will get a lot of things wrong, and that's okay.
Yeah.
For a lot of people, I think it's one of the first times you really start putting all of your effort into a curriculum, and it's hard.
Yeah.
And you think, why can't I do this? Am I not supposed to be here? But it's hard, and you just have to kind of rewiring your brain sometimes to, easier said than done, to recognize that it is challenging and failure or perceived failure is part of the process, and that you will never be able to understand everything, and that's okay.
Yeah.
That to me, I think, is personally what I have found the hardest.
I want to add to that, because I think you're right. One of the difficulties, and it's not related just to chemical engineering, but is that whole imposter syndrome that affects men and women, but it manifests itself in different ways. So it's very easy to think, I'm not doing well in this, so it means I can't do it. It doesn't. And, I always think like we push students to the limit of what they can do to some extent. And yet, if you asked a junior to take a sophomore level class, they'd find it easy because they've absorbed so much more than they really know. And they've now got more things that help them. It's almost like doing a jigsaw puzzle, but doing it like the backside out. So you don't know what the picture is. You just know that things slot together, and it isn't until you've got the whole thing slotted together that you really know what the thing looks like. Then, of course, you have to turn it over, which is another difficult thing to do.
That resonates a lot with me. And sometimes I kind of sit here and I'm trying to recall some core principle from some class that I learned. And I just can't sit here and tell you what it is, but then you kind of set me off on a problem and it'll just kind of pop up. So having confidence that you know that information is also challenging.
Mm-hmm. Another thing that it's not exactly what you asked, but I think it's related to what has come up now is to remember that science and engineering, and math, it's not one dimensional. It's not like you could say you're good at math or you're good at this, so you'll be good at chemical engineering, right? There's everybody has their own skill sets and talents, and like my brain, right? So like statistical thermodynamics was so easy for me. Quantum mechanics was so easy for me. Ask me to derive like the path of like 3 coupled pendula, and I can't. And linear algebra for me was so easy, it was ridiculous. But then geometry is really hard for me. I end up now working on stuff where I have to see in 3 dimensions, but that's because it was a challenge for me. But the thing is that you have to kind of figure out, and you do along the way, you will figure out like, okay, I'm pretty good at this, I'm really good at that, and I'm not so good at that.
Yeah.
You decide to get better at that, or you could just decide that, well, no, I'm going to play to my strengths.
Mm-hmm.
Right. And so, by aligning the things that you really love with also those things that you're really good at, right? That's where you're really kind of living your authentic life, I think, as a scientist, as a chemical engineer, right? Because you're and so to realize that it's okay if you're not good at this and this and that, because you're going to be good at this and this and that. And we need, all types to bring all of these different talents and skill sets and ideas to engineering.
Mm-hmm. Yeah, well said.
Thank you so much. I think this is going to be one of our final questions. What is your favorite part of being involved in the field of chemical engineering, and what specifically do you find the most rewarding?
Well, the most rewarding is
what we're
easy.
gonna say.
Yes, the most rewarding is working with students, whatever age, and high schoolers too. I have 3 Baltimore high schoolers who I'm working with, and they astound me. They are amazing. So I also, in fact, I said today that being with students is like the fountain of youth. Because you can't even feel old because you're immersed in all of these wonderful young people all the time, all day long. And I think that it really is just an incredible, so that experience is definitely the easy bit. What do I find the most challenging? I think communication is the hardest. You know, sometimes I wonder, am I speaking English? Because I thought I was really, really clear and I clearly wasn't. So, I mean, but, you know, my husband told me that in music, which I don't play any instrument at all, but I get the sense that he said, you can have, even if you know all the notes, the way that you play it is not, it's not identical for every person. And so, you know, I comfort myself with that to say, okay, there's intonations, there's, and you just have, so I think working on good communication is incredibly important, but it's also really, really hard.
Yeah, I think that gets to all of those things kind of wrap up into what I find the most rewarding is what, you know, people refer to as the aha moment. When you're basically, as Dr. Clancy is saying, you're playing, you know the notes, you're playing the song, and you are playing it in a completely different order than the students are hearing it. And then finally, once you figure out how to put those notes in the right order, and they're like, oh, that's Twinkle Twinkle Little Star. I don't know why I'm playing backwards this whole time. When you see that realization, like, oh, I get it, I can do this. It's just so rewarding to be a part of that journey. And I think that kind of highlights something that I generally like about chemical engineering, which is that as much as I can do in my own research lab in my small capacity, we are part of a community that we participate in and we actively work with, and we see the advancements of the people around us, and being able to participate in that and just kind of feel that sense of community is, you know, it just makes every time something doesn't work in the lab, you just, you know, one of your colleagues does have that aha moment. You kind of live through them for a moment. And I think that is, you know, so far one of my greatest joys from the field.
Yeah, the aha moments are great. Working with students is definitely, like, if I had to pick just one of the 17 things that I have to do in my job to keep, that would be the one, is working with students and doing research with students. Yeah, that's what I would say.
I will say from the more technical side, I think one of the most exciting things that when you start out in research, you have a lot of hypotheses that you test and they don't go anywhere. You end up realizing, no, that was never going to work, that was doomed. The first time that you think, I've read all this, I've tried these things, I think I have a good idea, and it just works, is just, there's no feeling like it. And so one of the things that I did during my PhD was I was trying to come up with a new way to make diesel fuel out of biomass derived ethanol. And I had some ideas and I tried some stuff, and eventually it worked. And that day, I think about that day a lot. I mean, honestly, probably no one's ever going to do anything with that fuel. But I still think about that day that I had an idea and it worked like I thought it was going to. And that's what chemical engineering allows you to do in action.
And persistence is really important in this business because things go wrong all the time. I mean, way more times than they go right. So you have to be the kind of person who says, you know, I'm not going to see this as failure. It's just something that didn't work. Now I have to rethink it. So it's like the problems are a puzzle, and you have to sort of work through the puzzle, and it's like trying to do Rubik's Cube, and you have to think of it from different ways, and so it's a challenge. It's like a mental exercise.
Mhm.
It'll keep you on your toes, but
Mhm.
it's fun.
Yeah, failure is just an opportunity to learn. And if you're not failing somewhat often, then that means you're not taking enough risk, right? You're not
Mhm.
asking hard enough problems. You're not trying to solve the really challenging things. Otherwise, you know, if they were easy, you know, everyone could do it.
Yeah.
So persistence is, you know, I'll take persistence over, you know, IQ any day.
Yes.
Thank you all for your answers. That was the incredible insight from Professor Clancy, Professor Eagan, Professor Glotzer. Since we're running low on time at this point, if any members of the audience has any questions or clarifications for our panelists, feel free to type them into the chat box. I see Professor Clancy has been answering many questions. Do any of the other professors have any insight about the questions in the chat?
Oh, I wasn't even looking.
Yeah, thanks, Dr. Clancy, because yeah, I have not been seeing these either.
Oh, look at that. Oh yeah, exactly. You don't have to be good at all of them. You just have to know a little.
I agree with all these answers. So.
What is your favorite element?
I love that question.
Oh.
I think silicon, it's the most important element, because we get semiconductors out of silicon. Yes, you could say gallium or whatever, but silicon, and you can get solar cells. It's the best.
But if you didn't have carbon, you wouldn't have anyone to use all that silicon.
Terrestrial people, extraterrestrial, based on a different element.
You asked that because of my periodic table.
Ah, yes.
That's what I'm thinking.
I gotta say, it's hard for me to pick. I play with the transition metals every day. Copper has a lot of cool colors, depending on what you do. And, you know, I'm a sucker for cool colors. Honestly, one of my main memories of high school chemistry was one day where we just lit like metal salts on fire.
Yes. Yeah.
That was such a fun day.
Wonderful.
And I know it's very simple, and I know it seems basic, but the other day we had a catalyst that was blue, and then we left it in air, and then it turned green. And I'm like, oh, that makes sense, and we can understand that. Mm-hmm. So I do like copper. It is, might actually be copper. But, you know, tungsten's fun, rhenium, palladium, platinum, rhodium, nickel. There's a lot.
That's not a favorite. That's a whole ensemble.
I guess it's hard to pick. I get very attached to them.
God, there's so
Sharon,
many good
you
questions.
never told us yours.
What?
Your favorite element?
Well, carbon.
Oh, carbon.
Oh. Yeah, I'm just looking here. There's so many great questions in here. There's one question about how do you come up with different research projects to work with, and who determines the research projects and who funds it, and which is a great question. So I have 25 PhD students usually at one time, and then a handful of postdocs. And so even though everyone has their dissertation project, they're grouped into themes, right? There's nobody in the group who's like working on something all by themselves out there that's unrelated to anything else, right? And so we have project areas, and some of the project areas are funded by the US Department of Energy, from the National Science Foundation, from the Department of Defense. They might be funded by philanthropies or foundations. I have funding from like the Simons Foundation. There's a lot of them that they give monies out to do research. And when I recruit a new PhD student postdoc to the group, I'm never bringing in a student saying, here's your project, go. I bring them in and I say, your job over the next month is to talk to every single person in the group, learn what they're working on, read some of the, the classic papers from our group, so you get more of a feel for things. And then once you've talked to everybody and you've seen all the research, you come to all these group meetings and you have a sense of all the different project areas. Now let's talk about what you're really excited about, right? Because everybody resonates a little bit differently, because I don't want to, I want to make sure that the project that we decide on for a student resonates with them, right? And builds on, utilizes their superpowers, right? Whatever that is, right? And so some people are going to do something that's much more theoretical and analytical. Some people really want to write code. And so we kind of figure it out together. As the leader of a research group, we're steering the ship, but it's a big ship, right? And so we're just keeping it going in a certain direction, right? But everybody is participating. I guess that's not like the perfect analogy, but but so you're setting a direction, right? And you might have some really specific ideas, but in general, the students, the whole point about a PhD is coming up with your own ideas, right? Coming up with a new idea that we didn't think of, right?
Mm-hmm.
And then pursuing that.
Maybe a sailboat, because then you're also at the mercy of the wind. So you might have the tiller in your hand, but you don't control the wind.
That's a good one. I like that. Someone else asked, what software do you use to generate the computer model? So my group, we develop almost all of our own software, just because we're asking what if questions about materials that there didn't already exist software to study with. And so our big code that we do our molecular simulations with is called HOOMD Blue, HOOMD-Blue, you can Google it. And it's now used by like thousands of people to do simulations of nanoparticles. And we have other codes too that we develop. And that's what we use. And we write our codes all like for GPUs, so we can squeeze every bit of every last cycle that we can out of it. And for many of our research projects, we're running on a computer called Summit at Oak Ridge National Lab, which is right now the largest open science supercomputer in the US, which is super fun.
I'm going to briefly jump back to the question about coming up with different research projects, in part because the only coding I do is with Python, some fairly simple stuff.
Good, that's good.
So I think this is a really interesting question, because I remember having it from an unnecessarily young age. I remember talking, I think I was in the middle school, I was a kid. I was just talking with one of my friends who mentioned that one of their parents had a PhD and they had a thesis. And that was the first time I was like, what is my thesis going to be? And I was like 10. I was like, why am I supposed to know what anything is? Like, I consistently had this concern, like, that would crop up every few years. Like, what am I going to do research on? I still haven't come up with an idea yet. I'm like 15. I don't know what I'm going to do. I don't have any research ideas. But you kind of just, things come at you. And I think that's just kind of the way you go through research, the way that I think I try to go through, to some extent you go through life, where you just see things and you learn things and you're patient, and random stuff will come up. You get excited about things, you try some stuff. It's a very organic process. The other thing I'll say is group dynamics definitely are very different between labs and universities. I just started my lab, so we have 2 graduate students, a postdoctoral student, and 4 undergraduates, and we are not going to get much larger than that. We might have a few more, but the size of groups and the dynamics of them are very different between different academic labs. And I have a high school student doing research in my lab right now. And he is doing a fantastic job of making all of these catalysts that I wish I had the time to do. And we are going to do all sorts of fun stuff with those. So I value the stuff that high school students do. One of the most fun experiences I had as a grad student was also working with a high school student. She was one of the smartest people I've ever met. I'm pretty sure. She knew way more than like above her pay grade, like questions. So yeah, high school students can really incredible.
I have a couple of high school students now, and I love, it doesn't matter how old. So the youngest we've had working in the group is 13. He's still doing projects with us. He writes computer code, and he already has a publication. He's already written codes for GPU that ran on Summit when he was 13.
Crazy.
I know. One summer he came back and grew like 2 feet. I'm like, we don't often have that big of a change in our students.
I wish that would happen to me.
Well, also to also remember a reminder to temper that a little bit with what Dr. Clancy was saying. I'm amazed that some of you high school students know that you want to do all this and you see these opportunities when you do. You don't need to. They'll come. You'll find them. Some people just have this innate understanding of exactly what they want to do. I understand that I think what I wanted to do better than a lot of people, but you'll find it.
Okay. Thank you guys so much for your insightful answers. I'm sure all the high schoolers in this meeting will be really pleased with that last series of answers, knowing that they're valued. I sure am pleased to hear that. So unfortunately, that's all the questions that we do have time for. It is 9:02. We got a bit over. Sorry to the professors for taking a little bit of extra time, and sorry to the audience as well. So before we close out, professors, do you have any final remarks, short bits of advice you would like to share with the audience?
I just wanted to answer this question about, do graduate schools care what research projects college students do? And I would say, when we're looking at graduate school applications, what you did the project on is irrelevant. We just want to see that you had research experience and that you loved it.
Yeah.
It could be on anything.
Yes.
So along that point, I think my kind of concluding thing for what I see as valued in research is somebody who is passionate and they have learned that to accept failure and be resilient. So try your best to be resilient when you see things, and just keep that passion and keep it kind of going strong, because that, in the end of the day, is what we're all here for.
My final thought is, again, to reiterate, do what you like doing. Don't end up doing stuff with people you don't like or things you don't like to do.
Yes, we're like, it's a very privileged position to be in, to be able to have a choice to do what you want to do with your life and with your and to have a career as opposed to a job.
Yeah.
And so you owe it to yourself, you owe it to society to pursue your dreams and follow your passion
and give back. I mean, I'm just riffing off of Sharon's comments there, but because the taxpayer pays for PhDs, and that's an enormous gift from them to you. Ask anybody who's had to pay for a master's degree. Getting a PhD for free is just this enormous gift from the taxpayers. So you owe them.
That's actually probably something we should make a point of, because I remember Professor Kate Stebbe from Penn telling me when she was an undergrad, she had no idea that she could get a PhD and get paid to do it. So when you get a PhD in the sciences or in engineering, you are paid to get your PhD. You are paid a stipend, your tuition is paid for. You do not pay anything.
That's great.
See, someone didn't know that. It is, we take it for granted now, but it's true. And I always start off when a new student joins my group, you know, I sit down and I tell them over the next 5 years, the US taxpayers are going to invest over $300,000 in your education.
Mhm.
You, what are you going to do with it?
And along those lines, there's an Angela Davis quote to lift as you climb. So
Oh,
that's
nice.
kind of what we try to do as we keep going up. We're looking and trying to help the people below us. So always to giving back is what everybody's saying. Just stay cognizant.
Well, thank you all for your wonderful closing remarks. On behalf of the whole BranchOut career panel team, we hope everyone enjoyed tonight's event and learned a lot about the field of chemical engineering. The chemical engineering field has become an integral part of our society and will continue to grow for generations to come. We would like to take a group photo with everyone, and you all have about 30 seconds to get ready for the group photo after we finish saying our thank you.
Yeah, once again, thank you so much to all our panelists. And we would also like to thank our other team members, Adarsh Bharadwaj, Ray Chen, Amelie Dang, Leroy Fu, Laila Ibrahim, Oliver Wong, and Kaya Jen. Thank you so much. As well as our project directors, Kavya, Victoria, and Evan. And of course, Dr. Wu. We wouldn't have been able to do this without you all.
Thanks, everyone. You did a great job.
Thank you so much. So